So I would also like to welcome you for the workshop and the colloquium. And the workshop is really a joint venture of somehow HITS, people at the university, at the Institute for Scientific Computing, and people within the newly funded Excellence Cluster structure. So it's nice to have everyone come together for this workshop here. And I would like to start with introducing our speaker for the colloquium, Professor Herbert Edelsbrunner. He is a professor at the Institute for Science and Technology in Austria. He actually was a student in Graz in Austria, but then spent more than 25 years of his career in the US, returning to ISTA in 2012. He has received many awards and distinctions. He also funded his own company, which is probably founded his own company, which is something which is not that typical in the academic setting. Among his many awards and distinctions, I would just want to mention the two most recent ones. So this year he received the Wittgenstein Award of the Austrian Science Fund and an ERC Advanced Grant. And so it's our pleasure to have you here, and we are looking forward to your talk.
Thank you very much for the nice introduction. I'd like to thank the organizers for inviting me here, giving me the chance to talk to you. I've never been in Heidelberg, this is the first time. It's a beautiful setting, I enjoy that. So as you heard, I'm from IST Austria. It's a startup university near Vienna. We started in 2009, and it's called an institute and not a university, even though we do teach and we have students, because we don't follow the Austrian university law. So the institute runs much more like an American system. We all speak English, including all the documents, and there's a small Austrian minority working there. Okay, so today I want to talk about stochastic geometry with a topological touch and also doing some experiments. So there's some results and there's some experimental data that might generate some conjectures. And I believe somewhere in the middle I even have some open questions. And I want to start with some prior work motivating what I'm doing. The general setting is I have a Poisson point process in Euclidean space. So what this is it's like a uniform distribution, a point sample. But uniform distribution requires a compact set. And I would like to have no constraints, no boundary effects. So the Poisson point process is the natural extension of that. All it says is that the chance of getting k points in some region is Poisson distributed. And if you have two regions or more that are disjoint, then the probability of getting points in there is independent. And there's a density rho, which is positive, which controls of how many points we expect in any area. And then here I just wrote down the formula. So there's the probability to get k points in some region omega. And by the way, I'll be picky about the notation. So omega will always be this region, rho will always be the density, n will always be the dimension of the space, x will always be this Poisson point process, the point sample. And so the probability to get k points is this expression. And maybe if you're not familiar with, let's set k equal to 0, for example. So the probability of getting no point in the region is, this is 1. Then it's the exponential, e to the minus rho times the size. So this double bar omega, that's the volume or the n-dimensional volume of the region omega. Okay, so the probability of not having any point in any region goes down exponentially. And I'm looking at the Warriner tessellation of the points. I would like to assume that you know what this is, but if not, each point gets associated a region, a neighborhood, namely the region of points where this generating point is the closest among the set. And then here's a little drawing. I pick n random points. And then I draw the bisector, perpendicular bisectors between the points. Because when I draw all of them until they meet, this gives me the diagram or the tessellation. I hope I don't get myself into trouble. Here's almost a degeneracy, but I got over it. Okay, so these regions are convex polygons. And the favorite object is then a dual called Delaunay mosaic. Warriner and Delaunay are two Russian mathematicians working 100 years ago, more or less. Some more, some less. So here I wrote that the Delaunay mosaic is the nerve. The nerve means that if two Warriner regions meet along an edge, I'm going to draw this as an edge between the 2 points. And this edge. And then if 3 meet, so these 3 regions meet at this point, I draw a triangle. It's not too much data here, so I can just finish this, I think. And then fill in all the triangles. So this is the Delaunay mosaic. Oh, by the way, I forgot to mention, I would prefer, if you have a question, ask it right away. I'm going to try to answer it short, so it's not a big interruption, but I prefer that over you getting lost, and then for the rest of the talk you just think of something else. Well, maybe that's also productive, but... In a plane, it's planar. The Delaunay mosaic is always straight embedded in a space it's defined in. So if you draw it in a plane, so here you didn't see any edges intersecting. It's not entirely obvious, but it's easy to prove. But this is also true in higher dimensions. So in 3 dimensions, for example, maybe I should mention that so you think about it, because the more interesting thing happens in 3 dimensions or higher. You have edges, triangles, and tetrahedra. Okay, they decompose the convex hull of the points in 3 dimensions. And there's no intersection between them. Here is an example of a Delaunay mosaic in a plane. The coloring is, I think the darker ones have circumcircles which are larger. This is some kind of threshold chosen, and the lighter ones are smaller. And this will have significance later. But yeah, so for a Poisson point process, they look like this. You could ask all kinds of questions. So one question I'm going to ask is, how many of the triangles are obtuse versus acute? And to remind you, an acute triangle is a triangle where all 3 angles are less than 90 degrees. Obtuse is one angle is larger than 90 degrees. And to simplify my life, I assume no angle is equal to 90 degrees. Because it's a Poisson point process, so the likelihood that there is an angle exactly 90 degrees is 0. Of course, it always happens if you don't have infinitely long real numbers, but probability 0. Okay, so here are some classical results. Let's see, what does this mean? So this is the expectation. D sub j is my notation for the number of j-dimensional simplices in a Delaunay mosaic. In n dimensions. And this is a constant, so the uppercase D, that's a constant. And we'll talk about this constant some later. Times the density times the volume of the region that you consider. Okay, and this was proved in 2 papers by Roger Miles. So he had some amazing papers in the 70s. Long papers, very much ahead of his time. Too much ahead of his time. I think then he didn't get tenure for some reason. There was some trouble, and he quit mathematics afterwards. He was discouraged. But those are seminal papers. Difficult to read, but a lot of results in it. This result here is actually easy to. It's not very deep, but it's already non-trivial because it says the number of simplices is proportional to the number of points in expectation. That's obvious in 2 dimensions, but it's not obvious in 3 dimensions anymore, where the number of edges, for example, can be quadratic in the number of points in general, not for a Poisson point process. Okay, and here are some of the constants. So let's see, if we go into 2 dimensions. So you saw the 2-dimensional picture. In 2 dimensions, there's nothing probabilistic about this question because there's the Euler's formula in a plane which says that the number of points minus the number of edges plus the number of triangles is equal to, depends on whether you use infinite plane or something, but I say equal to 0, since we don't worry about additive constants. And so here is for m vertices, I have 3 m edges and 2 m triangles, no matter how the points are distributed. Okay. But in 3 dimensions, this is not true anymore. So in 3 dimensions, the probability already kicks in, and it says, as proved by Miles, Meyering 20 years earlier also had these results, but he didn't have a proof, but he got the right constants. It says that the expected number of edges is 7.7 roughly times the number of the expected number of points. Each edge is incident to 2 points, so this means every point is, in expected case, incident to 15.5 edges. Okay, so you get a feeling for this. This is in a Delaunay mosaic. If you go back to the Warriner tessellation, the point corresponds to a polyhedron. An edge incident to the point corresponds to a face of the polyhedron. So this says, on the average, the Voronoi polyhedra have 15.5 faces. Okay, this is, by the way, pretty small. So it's close to what you get for lattices, for example, for the FCC lattice. I think you get 14. I forgot now, but roughly there. So it means that Poisson point process gives you more or less an equally spacing of the points. From these numbers, you can get even more. So, for example, here it says the expected number of triangles is 13.5 times the number of vertices. Now, a triangle is incident to 3 points. So, therefore, a point is incident to roughly 3 times this. So, that's 30.5.
Can you remember what J is?
J is the dimension of the simplex. So, which means here I'm looking at j equal to 2. So that's why I'm talking about triangles, the 2 simplices. So let's see, where did I want to go? Maybe I shouldn't spend too much time, but what I wanted to say is from this you can calculate the expected number of edges of a Voronoi face. Because the triangles correspond to edges of a Voronoi polyhedron, the edges correspond to faces, and then you can calculate with multiplicities, and then you get, I think, between 5.5 and 6 or something, which is also not obvious. So, but these are old results. So this is sort of the combinatorial side, old results, and then in the 70s the interest waned, and then more recently there's more activity again. And there's a second source of motivation for looking at these problems, which comes from actual 3-dimensional phenomena. So the motivation of these 5 people is the grain structure in metal. So apparently metal is organized in grains. grains are microscopic objects, perfectly packed atoms, but then the perfect packing cannot extend globally. There's too much stress. So then it falls into grains, and the grains somehow have more or less random position relative to each other, but internally they are perfectly ordered, and they have dynamics. Because if an atom is at the boundary of a grain, sometimes it might change its mind and then go allegiance with the other grain. And so typically the big grains grow, the small grains shrink, the whole thing courses. So that's the evolution for metal. And in the industry there's even a term for that. I think motors, for example, they get fatigue. So if the material gets fatigued, this means it's too far along this process, and then it's not up to the stresses anymore that it needs. And so so they are interested in this structure of the grains, which look a little bit like the Warriner polyhedra. They're not the same, but Warriner polyhedra is sort of a first attempt to get a feeling for it. So they have an experimental paper counting the average number of faces, or even the distribution of the number of faces, number of edges per face, the average number of faces of a neighbor. This is maybe I just mentioned the question. Namely, the question is, if you are a polytope with k faces, then look at your k neighbors, the polytopes that share these faces, and look at the average number of faces they have. And then the guess is, if k gets large, then your neighbors get small. Yeah, because you consume too much of the wealth, nothing remaining. And so there's this conjecture that this is really true. It's true experimentally, except that at the beginning it's actually not true, but there's no resolution to that. Okay, they also look at expected volume, expected surface area. An important property they study is sphericity of the grains of the polytopes. Sphericity is like how close is it to the sphere, and there's a mathematical formula for measuring it. Okay, so so far a little bit of the background, and now I want to go a little bit deeper into the stochastic analysis of these things. And maybe I should say where the topology comes in. So this has been studied purely geometrically, stochastic geometry, that's what it's called. We add a little bit of topology, and the motivation is this notion of persistence diagram, which I don't know, introduced 20 years ago, which I'm not gonna define today because you hear a lot about it in the afternoon anyway. But maybe you should know that a persistence diagram is in the background of the questions that we ask. The questions we ask is, when you have this growth process, how does the topology of the subcomplexes of the Delaunay mosaic, for example, develop? What can we say stochastically about it? And the main concept that I need for this is what we call the Delaunay radius function. So I have this script R, that's my function. It maps every simplex to a radius, a real number. And the definition is, it's the smallest radius of a sphere that passes through the vertices of the simplex and does not enclose any other point. So let me see whether I find an interesting sphere here. Yeah. So when I look at these points, A, B, C, I can draw a sphere around this point. Remember, this is by construction the center of the sphere, because this point is where the three Warriner regions meet. And therefore, this point is equally far from ABC, so it's the center of the sphere, or circle in this case. All the other points are further away by construction, so there's no point inside. So this radius is assigned to this triangle. Another interesting case is maybe this here. D, E, C has already a name, E. In this case, the circle is very big, although the triangle is not so big, because the center is down here. The whole thing is already a little distorted. But so the sphere that I'm talking about is not the smallest sphere that surrounds the simplex, but rather it has to pass through the vertices and it has to exclude other points on the inside. Okay? And then we're interested in this sublevel set. So what this is the collection of all simplices such that the radius is at most r. And we call this the alpha complex for radius r of the point set x. I'll show you an example. Here's a point set. I'm going to grow some disks. So let me call this radius r now. I decompose this with the Warriner tessellation, or the part of the Warriner tessellation that's inside the union. And then I take the dual of that. And these are exactly the Delaunay simplices whose radius is less than equal to r. Okay. And I can increase the radius a little bit. And then the Warriner region gets exposed a little bit more. So I get some more neighborhoods or regions that meet in pairs or in triples. And therefore I get more simplices. And the color shades the new simplices. And I want to point out a few things about these simplices. Like here, this triangle and edge. This came about because here this Warriner vertex gets swept over by the union of disks. And so this vertex and this edge get exposed at the same time. And therefore I add the triangle and the edge at the same time. This is called an anti-collapse sometimes. So it just thickens the shape. It doesn't change anything topologically. And most of the changes that you see are this way. So up here I have a triangle and edge and then another triangle and an edge. Okay, so this thickens locally. The only change that actually changes the topology is up here. There's an edge without a triangle next to it. And because I connect this edge, I connect two vertices which were already in the same component, so now I form a loop. Okay? And because of this distinction, these things have names. So this edge here is called a critical edge. And the other simplices that we added as pairs, triangle edge pairs, they're all called non-critical because they do not change the topology. And this kind of process is also in higher dimensions. Let me just go briefly to 3 dimensions. So when you grow balls and then you create the alpha complex and then you add Delaunay simplices, then those either come a single simplex, then it's called a critical simplex, or they come in pairs or in 4 tuples. I'll show you the 4-tuple case a little bit later. 4-tuple case is when a tetrahedron together with 2 triangles and an edge come at the same time. It's also called a collapse. And so all these composite appearances, they do not change the homotopy type. That's a technical term for the topology. Okay, so therefore the critical simplices are important, and I'll say more about them. Okay, and then when a growth goes to infinity, then my alpha complex is entire Delaunay mosaic. All right, so let's go back to this radius function. And what I said earlier, the increments of the radius function, the increments of the sublevel set are what I call intervals, or in general what are called intervals. An interval is, for example, a pair or a single simplex in 2 dimensions. So it's always given by a lower bound, that's a simplex, and an upper bound M, that's another simplex, and it consists of all the simplices in between the 2. So for example, the lower bound could be an edge, and the upper bound could be a tetrahedron that has this edge as an edge. And then I also add the 2 triangles that have the edge as a face and that are faces of the tetrahedron. So these are the intervals in general dimensions. And I write little l and little m for the dimensions of those, because that's going to be important for the counting. And now it turned out that counting these intervals is easier than counting Delaunay simplices. I guess we were lucky. So we get nice formulas for these intervals, and then we can get the formulas for the Delaunay simplices as consequences. So this way, by focusing on a topology, we could even improve our knowledge in geometry. So the general result looks like this. The expected number of intervals with lower bound dimension L, upper bound dimension M, let me ignore the R here, is this constant C sub Lm times the expected number of points. And then if I bound the whole thing up to radius R, I get this coefficient, which is a ratio of gamma functions. So below is the gamma function, that's m minus 1 factorial, and above is the right incomplete, I believe it's called, gamma function. The gamma function is defined as an integral, and this little gamma is just a partial integral. So if the second parameter is infinity, it's the complete function, and then the ratio goes to 1. Okay? So this way we don't only get the numbers, we also get the dependence of the numbers on the radius that I give. And then here is the translation into the constants for the Delaunay mosaic. So it's, since a J-simplex is in various intervals, so it's a kind of a sum of those, that's not surprising. But again, I also get the dependence on R. So there's two new results. One is getting some extra constants in 4 dimensions, and the other one is dependence on R, which I've not known before. And this is the work with Anton Nikitenko, one of my co-authors. The other two co-authors, that was Kati Ölsberg and Peter Sinak, they did extensive experiments. So I'm going to show you soon what they did. Okay, so here is 2 dimensions, expected numbers depending on R. So the horizontal axis R, the vertical is the number of simplices. And we see that the number of critical triangles, that's 2, 2, is equal to the triangle edge pairs at every radius. That's cool. Oh, before I go on, I did want to talk about this a little. Namely, remember at the beginning I talked about acute and obtuse triangles. Here is an acute triangle. When you do the Warriner decomposition of an acute triangle, the Warriner vertex is inside the triangle, and therefore this triangle is going to be critical because the disks starting at the vertices, they're going to grow together, but they're going to meet pairwise before they meet triplewise. So the acute are critical for our radius function. The obtuse triangles have the Warriner vertex outside, and therefore obtuse triangles are non-critical. Oops, non-critical. Why is that? Because when I grow the disks, at some moment it will look like that. And then they grow towards this Warriner vertex, and when they reach the Warriner vertex, then at the same time we reach the edge and the triangle. So this is the non-critical case, it's an anti-collapse. Okay, so these probabilistic results tell you about the likelihood of obtuse and acute triangles. And let's go back. Here it says half the triangles are critical and half the triangles are paired with edges. So this means probabilistically half the triangles are acute and the other half are obtuse. Not entirely obvious why that is, but it's this way. Here are the graphs for 3 dimensions. The graphs usually just start with the edges because the vertices, they all start at beginning, so I don't show them. But one thing you see here is, for example, the 2, 2 and the 1, 2, they have the same maximum. That's why we color the graphs in the same color. And the reason will become obvious soon. So the important thing is actually the maximum, the upper bound in the interval. So both are triangles. The next case here is the tetrahedron. So tetrahedron critical, tetrahedron paired with edge, tetrahedron paired with triangle, paired with edge. And they are just multiples of each other. And then here you get the constants. So from these constants, you can derive directly the constants I showed you earlier for Delaunay, which have been known 50 or more years ago. For example, the Delaunay edges is just 4. These are critical edges. The edges I get from paired with triangles, 2.55, and the edges I get paired with tetrahedra. And so that's together 7.76. If you remember, that was and the other constants you can get this way too. The new thing is 4 dimensions. So in 4 dimensions, the constants have not been known, but we have been able to get the constants. So here are the graphs, here are the constants, and you can get the numbers. So now in 4 dimensions, we also know the number of simplices of every dimension of the Delaunay mosaic. Maybe you don't care, so I'm not going to delve into the numbers, but I think it's really important. That was a joke. Well, actually, maybe not. Who knows? But instead of getting into these numbers, there's a nice combinatorial argument that leads to these numbers. And I wanted to show you this combinatorial argument. It's due to Wendel from 1970 something. Let me first do it in two dimensions. So the entire proof to get those constants is integral geometry, lengthy expressions, and then there's a combinatorial part, and this is what I'm talking about. And the question here is the following. Suppose I give you a circle, unit circle in a plane, and you pick 3 points at random uniformly on the circle. Now I ask, what is the chance that the triangle formed by these 3 points contains the center of the circle? Any suggestions? Don't be shy. What? More than 50%. You want to bet 10 euros? How much? 50%? Same offer? 25? I don't offer you any euros. He knows. No, it's 25%. That's correct. Did you know, or just a guess? I give you a proof. There are several proofs. So here's the proof by Wendel. It's nicely symmetric, so that's what I like. Namely, first, I'm going to draw my triangle, my 3 points so that it contains the center, like here. And then I can decompose my triangle into these 3 cones, and I call the areas little a, little b, and little c. Okay, so the area of my original triangle is a plus b plus c. Okay, now what I'm going to do is I'm going to reflect the point A through the origin to the other side. B and C stay the same. So I call the new vertex minus A. So I have a triangle minus A, B, C. And if you look at the cones that I get for the new triangle, this cone between 0, C and minus A has area little b, because it has the same base as this earlier triangle, and it has the same height. So therefore it's the same area. So this is little b. This triangle has area little c, same as here. And this triangle has area A, but now it's negative because it's outside my triangle. So the new area I get is minus A plus BC, plus B plus C. And this is a general theme. So whenever I reflect a vertex, I get the area negative. So I can do this, well, I can reflect A, B, C, so 3 times. And then I can reflect 2, A and B, A and C, and so on. So I get 8 combinations. And then, so there you see the areas. Of course, they are signed areas, because if I have minus A, minus B, minus C, that's certainly a negative number. So I have to take the absolute values. But the important thing is that if 2 of those sectors come with a different sign, then one of them is outside the triangle. And therefore, the triangle cannot contain the origin. Only if all the cones come with the same sign, so this is A plus B plus C and minus A minus B minus C, the triangle contains the center. So that's 2 out of 8, 1/4. Convincing? Okay, then let's do it in 3 dimensions. In 3 dimensions, we could have the center inside of the sphere. So, okay, 3 dimensions, what it means. We have a sphere, we pick 4 points randomly. We take the convex hull of the 4 points, that's a tetrahedron. We ask, is the center inside of the tetrahedron? It could be inside, or it could be outside. And when I look at the tetrahedron from the center, I see a triangle. Or when I look at the tetrahedron, I see 2 triangles. I cannot see 3 triangles, because otherwise the points would not lie on a sphere. So these are the 3 cases. And then I do this reflection business, so I get 16 combinations. They give me sign patterns, and the center is contained in a tetrahedron if the sign patterns are all pluses or all minuses. That's 2 out of 16. So it's 1/8 is the probability that it contains the center. But I need more information. The probability that my center sees 1 triangle is 1/2. Because that happens exactly when the sign pattern is 1 plus 3 minus, or the other way around. And when there are equally many signs, pluses and minuses, I see 2 triangles. Okay, so these are the probabilities. And that you have to do in every dimension, so we do it in 4 dimensions and still get some results. Okay. Maybe at this point you would ask, why do I not know the numbers in 5 dimensions? But since you don't ask, I'll talk about something else. Related, of course. The difference between critical and non-critical simplices is important, as we said earlier, because as we grow the alpha complex, the critical simplices change the topology and the others don't. And so I write here 1 stands for edge, because 1 simplex, minus stands for killing, plus stands for giving birth. So I need to explain this. So I'm now focusing on the critical simplices only. The others I ignore. And when a critical edge comes into the picture, there are 2 possibilities. Either it connects 2 vertices in different components. Then, by drawing this edge, I lose 1 component. I call this a death of a component. And so it's counted as in 1 minus. It could also connect 2 vertices which are already in a component, and we form a loop. So we get 1 more loop. So that's a birth of a loop. Okay? And when a triangle in a plane comes in, it always fills a loop. So it's always a death of a loop. Okay? Oops. So here I'm looking at the number of critical simplices, distinguishing giving birth and distinguishing death. And if I add them up, I get the number of critical simplices. But for me, it's really important to know how many births, how many deaths. And the reason is, sorry, that was an experiment, but it didn't work. When I subtract the birth-giving p simplices minus the death-giving p plus 1 simplices, then I get the Betti numbers. Okay, so from the earlier curves, I did the subtraction. Now I get these Betti numbers. So these Betti numbers, that would be a really nice goal of figuring out how they are distributed. But unfortunately, this is pretty complicated, so I don't think there's much hope. But experimentally, we can give you the pictures. And then we did the same thing in 3 dimensions. So there, even the triangles can give birth and death. So the triangles, death is if it fills a tunnel, so you cannot fly through it anymore. And the birth is when it closes off a void, the last tunnel in a domain. And again, so here are these curves. And here are the Betti numbers. And so computing analytic expression for these Betti numbers, I think is probably out of reach, but this would be a really nice goal. But we would, when we go back to the persistence diagram, we would ask even more difficult questions, such as also when you look at the tunnel, for example, you ask how long does the tunnel exist in this alpha complex for radius r, so for what range of r. Because if it lives for a long time, its contribution to these curves is bigger. And to sort this out, but I'm not getting there because it's too hard a question. Okay. So let me say something about weights. And maybe I'm going to speed up a little bit so I also can say something about wrapping. Weighted Delaunay mosaics and weighted Warriner tessellations are not as popular as the unweighted versions, but I think justifiably one. So they're kind of my favorite. So this is what you see here is a weighted Warriner tessellation, and let me tell you of how this can be computed. You could take a point set in 3 dimensions, say Poisson point process in 3 dimensions. You compute the Warriner tessellation in 3 dimensions, and then you slice this thing with a random plane. And what you see is a slice. Okay, so this is a model for weighted Warriner tessellation. And the weight comes from the fact that if a point is further away from the plane, then its influence on what happens in the plane diminishes. Until if it's very far away, it doesn't even show up anymore. And the closer you are to the plane, the more impact you have. That's the weight. And somehow for example, you see sometimes you have 2 points in the same Warriner region. The reason is, in the weighted case, a point doesn't even have to be inside of its own region. I show you also one, if I remember right, this is from 10 dimensions. So what I just told you about 3 dimensions, you can also do it in 10 dimensions, where you take a 10-dimensional Poisson point process, and then you slice the 10-dimensional Warriner tessellation with a 2-dimensional plane. You also get the weighted Warriner tessellation. The statistics is a little different. And how it's different, that's somehow the question that we ask. Now, I want to say a little bit about why some points are not inside their own region. This even happens in 1 dimensions. So my notation is always the Poisson point process is in n dimensions. I take a k-dimensional slice. So this way is a k-dimensional Warriner tessellation. So that's of course just an alternation between vertices and edges. You could think of it this way. The points are in 2 dimensions. The tessellation is in 1 dimension. And then you can imagine moving the center of a circle along this line and drawing the circle always just as large as you can until it hits the first point. And so you see when a circle is like this, where the 2 points lie on the left side, then the bisector here goes beyond the center of this circle. So here, the point that generates would be outside its own region. And you see down here, when you go to the Delaunay mosaic, you have a critical vertex, then there come edge-vertex pairs. And then comes a critical edge, then come vertex edge pairs, and then comes a critical vertex. So, and there's no freedom. So the alternation is always like this. And so here I give you numbers. So this is the edge vertex pairs. So it's roughly a quarter. And of course the vertices and the critical edges, they are the same numbers. This is in 2 dimensions. Let me not get into the numbers. I wanted to mention these 2 equations down here. I do not know whether they are true. They seem to be true from a lot of experiments. They look like Euler formulas, but probabilistically. They're not true for non-Poisson point processes. But I don't have a proof for them. So this says, for example, C22, let's see, that's here. This 1.73, that's the number of critical edges in 2 dimensions. Sorry, critical triangles. Is equal to the number of critical vertices plus the number of vertex edge pairs. And here's another equation. So these are my open questions for today. Why are those true?
Do you have this conjecture also in other dimensions, or is it specific to n3?
This is in all dimensions. I mean, as far as we did the experiments.
Then it's something like Cij is the sum of all 0.
Oh, a general formulation of this? I don't have that. So I just extracted those 2. But these 2 are true in all dimensions as far as I know. I mean, for k equal to 2 and n anything. And this graph I wanted to talk about a little bit. This shows the expected length of Delaunay edges. So that's about the distance between points. And the different graphs come from varying n. So let's see, I think k is equal to 1. And n is equal to 2, 3, up to 10. And then what you see is 10 is the steepest curve. It shows you that if n gets larger, the distances get more concentrated. And this points to the fact that when you do this weighted experiment, the points that generate the regions, they are not Poisson point process distributed anymore. Which is kind of strange because we constructed them this way, but we constructed them in n dimensions. And then after that, we projected them. And by projecting, some of them don't even get projected because they have no influence. So they disappear. And then this means the ones that remain, they are a little bit better distributed because they somehow the distances are more focused. So there's a subtle repulsion between the points that comes from this construction. But the repulsion is not physical, it's just geometric. And this is also another analytic result, namely the following experiment, that you have a Poisson point process, you grow disks, and then you draw a straight line, and then you ask how many components do you have? Because you alternate between you're inside the disks, inside the union, and then you're outside the union, inside the union. And this has an analytic expression. At first we were very excited because we could get this, namely by just observing that the only way to go inside and outside is if you pass a critical edge. The non-critical edges, they just thicken things. And then because we have analytic expressions for everything, we can just put it down. But there has been a proof of that earlier, completely different proof without topology, but this was known. But you see nicely how this concentrates, and then as n goes to infinity, it's get the same distribution. Okay, last topic, wrap. This relates, in fact, to my company that we started in 1996. The goal there was surface reconstruction, that I scan an object, like your face, and then I would like to reconstruct the surface from the point set. sounds very intuitive, but it's not so easy a problem. So I had an idea of how to do it. This is the algorithm. And didn't publish it because we started a company based on it and nobody could repeat it. Now I can tell you how it works. After all these years, there's a very simple definition. Namely, what you do is you take the alpha complex for your favorite radius r, and after that you collapse as much as you can the intervals in the Delaunay mosaic. And for example, I think this point set I generated myself. This is a monkey saddle. It's a degenerate situation from this differential geometry. And this is literally the first attempt. So this is r is equal to infinity. That's the complex. It's a nice triangulation in one step. There's no complication, no cases, nothing. So I personally am very interested in getting to know a little bit about the statistic of this wrap complex, just because it obviously gives nicer results. They are practically useful. Proof of that is that people pay for it. And it's harder to understand. I mean, the definition is short, but to predict what it does is not so easy. So we did some experiments. And let's see, this is in 2 dimensions. The number of intervals. So 1, 1, that's the critical edges and the critical triangles. And the critical edges and critical triangles are exactly like in the alpha complex. There's no difference. Just you see it by the definition. But if a simplex is not critical, so it's subject to collapsing, then it depends where it is. Because if it's somehow close to the outside, I can collapse it away. But if it's protected by another critical simplex, I cannot collapse it. So that's now a difficult question. And we see actually the curves we get are very nice. So this dashed line is the edge triangle pair. So it's just shifted. In the alpha complex, it was closer by, and then it's shifted because most of the time I collapse it away until they get protected. And then here is a comparison, the wrap complex in solid and the alpha complex in dashed. And from the difference, you see how much gets collapsed away. So this is the edges that could collapse away, and here's the triangles that collapsed away. So for example, it must be that the curve between the dotted and the solid here, this integral, is equal to this integral on that side, because eventually it goes to 0. Yeah.
Why does the number of simplices in the wrap complex become larger than the one in the alpha?
It doesn't become larger. The number is the integral up to that point. It just means the increment is larger, but the wrap complex is always behind. Yeah, I mean, I could have shown but those curves are much harder to understand. So this gives the density, and if the number is then integral. Yeah. Thanks for clarifying that. 3 dimensions. Here you see one phenomenon that I mentioned earlier. In the alpha complex, we had the curves with the same color had the same maximum. This is not true anymore. Of course not, because the critical, they stay where they are, but the non-critical shift. And now you also, so here you have again this difference, and where the integral comes in. These curves that we get for the wrap complex, they seem very nice. And then also we somehow experimentally tested whether this is possibly a gamma function or a linear combination of gamma functions. And it looks like maybe they are. So maybe there is actually an analytic expression for them, but I don't have it. By the way, I should have mentioned maybe something earlier. The reason why topology helps in stochastic geometry, I think it boils down to the following. When you look at the Delaunay simplices, and as they are distributed as a function of radius, they are not gamma functions. they are linear combinations of gamma functions because the intervals are gamma functions and the Delaunay simplices, as I showed you, are combinations of intervals. And because they are linear combinations of gamma functions, they are kind of harder to get to until we stumbled into the intervals which are gamma functions, and then it become easier. And that's all I wanted to say. Thank you.